All right, let's dive in. The goal today is to really get the big picture of what's going on with your data. Look, before you get completely buried in formulas and different statistical tests, we're going to talk about the why behind it all. By the time we're done here, you won't just be clicking buttons to run a test, you'll actually understand what it's all telling you. So, let's get into it.
It all really kicks off with this almost impossible sounding question. I mean, think about it. You see it all the time. A pollster talks to, 2,000 people, and then they go on TV and say what an entire country of millions thinks? How on earth does that work? How can a tiny little slice tell us anything meaningful about the whole pie? Well, the magic word here, the whole concept this is built on, is inference. This is the absolute core mission of pretty much all survey research. We grab a small, manageable group, our sample, with the big goal of saying something smart about the much, much larger population it came from. The whole trick, of course, is making sure that our little sample is actually a good miniature version of the real thing. So that's the name of the game, bridging the gap between the people we actually talk to, our sample, and the giant group we want to talk about, the population. And to do that, first we have to get a handle on just how different our little sample might be from the real deal. And that difference, that gap, has a name: sample error. In a perfect world, we just take our sample's average, subtract it from the true population's average, and bam, there's our answer. A tiny difference means very little sample error, which is great. It means our sample is doing a good job. But a big difference, well, that means our sample might be leading us way off track. And right there, that's the big catch, isn't it? I mean, the entire reason we're doing a survey in the first place is because we don't know the population's average. If we already knew what everyone in the country thought, we wouldn't need a sample at all. So how in the world can we measure an error that's based on a number we don't even have? It feels like a total paradox. Okay, so we can't measure it directly, but what we can do is make a really, really good educated guess. We can estimate it, and lucky for us, statisticians have come up with some pretty brilliant tools to do exactly that. And the number one tool for this job is called the standard error. You should think of it as our best possible guess for that real, but unknown, sample error. It's a number we actually calculate from our own sample data. And it tells us, hey, here's how much we think your sample's average is likely bouncing around the true population average. So how do we get to this awesome number? Well, it's kind of like a three-step journey. We start with something called variance, which gives us a raw number for how spread out our data is. The problem is, it's in squared units, which is weird and not very intuitive. So, step 2, we take the square root of that to get the standard deviation. Now we're talking. This puts the spread back into units we can actually understand, like dollars or years or whatever we're measuring. And then finally, we use that standard deviation to calculate our real prize, the standard error, our best estimate of the sample error. So look, if all that is making your head spin a little, just burn this one thing into your brain. Big standard errors are bad. They mean our estimate is wobbly and uncertain. Small standard errors are good. They mean our sample average is probably really, really close to the true population average. That's the gold standard. Okay, cool. So we've got our tools, we can estimate our error. We're all set to go, right? Well, not so fast. Because sometimes the most basic number we calculate, the average, can be lying to us. Big time. Let me throw a real-world example at you from the General Social Survey. It found that the average number of lifetime female sexual partners for an adult in the US is 5.6. Okay, it's a number. But does that number really tell us what's going on? And bam! One look at this graph tells you the story. Just look at this thing. Almost everybody, the vast majority of people, are clumped way down here on the left, near 0, 1, 2. But the graph has this super long tail stretching way out to the right. That average of 5.6 is floating out here in no man's land. It doesn't really describe the typical person at all. So what is happening? The villains of our story are outliers. These are those really extreme data points that are so different from everybody else, they can literally grab the average and pull it way over in their direction. It's like a statistical game of tug of war, and one or two really strong outliers can drag the mean away from where most of the data actually is. So what's a researcher to do? Well, you gotta roll up your sleeves and do a little data cleanup. Before we can trust any of our fancy calculations, we have to find these outliers that are messing everything up and deal with them. So how do you actually hunt these things down? It's like being a data detective. First, you look for your big red flag, a huge standard deviation. That's clue #1. Next, you compare the mean and the median. If they're really far apart, something's fishy. That's clue #2. Third, you run a frequency check to see the raw numbers and find out exactly who these extreme cases are. And finally, once you've found your culprits, you can tell your software, hey, just ignore these for now, set them as missing. And here is our first clue in action. The stats table on the left is practically screaming at us. The standard deviation is almost 18. That is gigantic, especially when you remember the average was only around 5. Then you glance over at the histogram on the right and you see exactly why. It's that long, flat tail caused by just a few extreme cases. The number and the picture are telling the exact same story. Now for clue number 2, and I love this one. Think of your data like it's all sitting on a seesaw. The median, the person exactly in the middle of the line, is at 1. That's our balancing point. But the mean, the average, is way over at 5.39. That tells you there must be some really heavy values sitting on the far end of the seesaw, pulling that balancing point way up. And this is where we find the smoking gun. A frequency check lets us just look at the raw counts, and you can scroll down, and there it is, 1. Single person reported 700 partners. Just one individual. But that one unbelievable answer has a massive effect on the whole dataset's average and its standard deviation.
So, what happens after we tell our software to ignore that person and a few other extreme cases? Well, the change is just dramatic. Look at this. The mean drops from 5.39 down to a much more reasonable 3.04. But the real story is the standard deviation. It absolutely plummets from a crazy 17.68 all the way down to 5.02. That's a game changer.
And this right here is a huge win. We now have an average that actually feels like it represents the data. And by slashing that standard deviation, we've also made our standard error way smaller. And what did we learn? Small standard error is good. It means we can be much, much more confident when we make that inferential leap from our sample to the whole population.
So, there we have it. We found the problem, we cleaned the data, we got rid of the outliers, and now we have a new, much more realistic average with a much smaller error. It really seems like we can finally trust our answer, right?
And the source material seems to agree. It says right there we can have more confidence now in this reported average. It feels like we've done our due diligence, solved the statistical problem, and arrived at a better, more accurate truth. But then, the text leaves us with this final little cliffhanger. Or can we? It makes you stop and think. Even after all this careful statistical work, is there maybe another problem, something deeper that we haven't even thought about yet? What else could be wrong with this data? That's a great question to keep in the back of your mind as you start your readings. Thanks for tuning in.